If you think that artificial intelligence was recently invented, think again. The roots of AI go back decades, centuries, even to ancient mythology. So how did AI go from myth to reality? Hello, you're listening to Where What If Becomes What's Next from Carnegie Mellon University, where we're exploring what AI means to industries, government, society, and you. Today's episode is the first installment of a two-part series focused on the birth of AI and then its future. In this episode, we learn about the history and even the prehistory of artificial intelligence and the exciting role that CMU played in AI's origin story. To talk about how artificial intelligence, as we know it, came to be, we first have to go back thousands of years when ancient thinkers first started to ask, what if we could do more? Recent scholarship argues that Greek mythology was foundational in shaping society's thinking and dreaming around artificial intelligence. Take the myth of Talos, for example, one of, if not the first imagined robot. The king of gods himself, Zeus, commissioned the building of Talos, a large autonomous robot man forged of bronze and powered by the god's life force to defend the island of Crete. Scholars say the story of Talos shows just how far back human fascination with artificial life goes. By the Middle Ages, and then the Renaissance period, philosophers and mathematicians like René Descartes, known for saying, "I think, therefore I am," theorized and debated the ethics of creating machines that mimic human capabilities. Fast forward to the 19th and early 20th century, when pioneering mathematician George Boole in 1841 formulated the basic rules for what would become known as the Boolean algebra, the early roadmap for digital logic circuits and computation. Then there's Alan Turing. The British mathematician published a key paper in 1936 titled On Computable Numbers. In this influential paper, Turing theorizes a universal machine that could execute complicated mathematical tasks, essentially paving the way for modern-day computer science. Turing also introduced an experiment in 1950 that assesses how convincingly a machine can demonstrate human-like intelligence. It came to be known as the Turing test. But the birth of AI as a distant area of scientific research is attributed to the Dartmouth Summer Research Project. In the summer of 1956, a group of researchers convened for a research workshop at Dartmouth College to discuss how human intelligence could be broken down, both to better understand it and to reproduce it in machines. Organizer and then Dartmouth mathematics professor John McCarthy is said to have coined the term artificial intelligence at the conference, earning him the moniker as the father of AI. Two researchers presented a paper on an AI algorithm to the conference attendees, Herbert Simon and Allen Newell, collaborators and professors from Carnegie Mellon University. At that time, they were working with a systems programmer at the RAND Corporation, developing the information processing language, the first list processing language for computers. With that same systems programmer, who was named Cliff Shaw, they also created the first program to perform automated reasoning, known as logic theorist. Simon viewed AI as a unique tool to better understand ourselves, not to replace us. Here he is speaking at the Earthware Symposium at CMU in 2000, several months before his death.
Of course, it's not really electronic knowledge. It's knowledge about the creation, transmission, and processing of information. And thus, it gets to the very roots of our own humanity. It's knowledge about ourselves as thinking individuals and as communicating collectivities. It's given us a whole new picture already of what the human mind and what the human thought processes are all about and how they're carried on.
He goes on to say he'd like to see newer technology being developed and used to, again, better understand ourselves, but also to address the problems most central to our world.
Problems about our ability to govern our own conduct in using the world's resources and conserving it as a life-maintaining planet, and most of all, problems of governing our relations with each other.
Similarly, Simon's collaborator and colleague, the late Allen Newell, described his work in computer simulation as being driven by an unwavering desire to understand the human mind. Newell touched on this in a 1991 talk delivered at Carnegie Mellon University.
A scientist is a transducer from nature to theory. Don't kid yourself that you have very much to offer. Your problem is to go listen to nature, transduce what it has to say into a theory, but don't believe that the theory is coming from you. It's coming from nature. So the name of the game is to seek out nature and listen to her.
Simon and Newell would go on to jointly win an A.M. Turing Award, considered the highest accolade in computer science. Simon would also earn a Nobel Prize for Economics in 1978. And their research would also cement CMU as a critical player in the history and advancement of artificial intelligence.
They were instrumental in getting AI going in the world. They were also instrumental in, I think, convincing CMU to make a big bet on computer science and AI as well, as early as the 1960s.
That's CMU Founders University professor and computer scientist Tom Mitchell. When Mitchell arrived at the CMU campus in 1986 as a visiting professor, he had the chance to meet and work with Allen Newell.
And after we got to know each other the first semester I was here, he said, well, I'm thinking of teaching a course at AI in the spring. Why don't we teach that course together? So I thought that was a great idea.
Newell had also asked then CMU assistant professor Jeffrey Hinton to co-teach the class. Years later, Hinton would go on to become a Turing Award winner for his pioneering work on neural networks, which are a foundational element of artificial intelligence and are designed to function similarly to how the human brain works. The three taught an advanced seminar on AI that they called Architectures for Intelligence, and Mitchell says it was a hit.
At the end of the year, we all agreed I should just stay here, and I've been here ever since.
Originally interested in human intelligence and thinking he'd pursue a degree in psychology, Mitchell found himself more drawn to building intelligent systems and computers once he learned the tech to actually see inside the human brain did not yet exist. He, in part, credits the late computer scientist Arthur Samuels, another pioneer of AI research who worked at IBM in the 1950s and 60s. Samuels is best known for the programming work he did in which computers learned from experience.
And he had written a computer program that learned to play checkers. It was given the rules of the game, but it learned a good strategy. And it learned by playing games against itself. And I thought this is the most amazing idea. So in one of my course projects, I did a baby version of that, building a system that learned to play three-dimensional tic-tac-toe. But once I saw that this was actually a feasible thing, that it wasn't sci-fi, it was something you could really do, I was totally hooked.
By the time Mitchell got to CMU in the 80s, he was fascinated by different kinds of machine learning.
When I say machine learning, what I really mean is getting computers to improve their performance at some task through some kind of learning experience. And so, for example, we worked on getting robots, these were very primitive robots in the late 1980s, to drive around the room and look for cups to pick up. But the robots would get better and better at doing this with more and more practice. For example, once it found some cups, it would learn to recognize them from further away, because once it knew that was a cup, then it could go back and see what the cup looked like from 3 feet away, from 8 feet away.
Tom, I want to jump ahead a number of years to the late 1990s. There's a fair amount going on at CMU around machine learning within the university's School of Computer Science, and you start to get some interest from the statistics department on campus. Tell me more about that bit of history and its significance.
There was kind of a growing awareness between the statisticians and me and others in computer science that statistics should play a more foundational role in machine learning than it had up to that point. And so we created what was initially a research center. I wanted to call it the Center for Machine Learning, but the statisticians hated that idea because at that time, machine learning was viewed as a suspect field of study by the statisticians. Didn't have enough theorems underlying it, apparently. So instead, we ended up with the Center for Automated Learning and Discovery.
I understand things really took off, and within several years, the center offered a master's degree program, a PhD program in machine learning, and you had dedicated faculty. Then, in 2006, you went to university leadership to make your case for turning this center into an official department. What did you say?
What I anticipated was that I would go to the administration, the provost and the deans would look at this and they would say, well, you can't do that because we already have a statistics department. There's too much intersection. We already have a computer science department. They didn't say that at all. What they said was, you cannot have a new academic department unless you have a scientific discipline that's going to be here 100 years from today, which was a great challenge to be given instead of the politics of turf wars. And so we went off and wrote a white paper called The Discipline of Machine Learning, a short white paper, but it explained what the field was, how it related to other fields like psychology, evolution, statistics. And the deans read it, the provost read it, I think the president read it, and they said, okay, you're in.
So in 2006, CMU launched an official machine learning department, believed to be the first of its kind in the world, though by no means the first spin-off department from the School of Computer Science. I think the first was actually the Robotics Institute, and there are others like the Language Technologies Institute. The university took a gamble on these fields because leadership felt they'd become more important in the future. But how do you think views on AI research and thinking evolved since the Dartmouth workshop in 1956?
Over the decades where AI was developing at CMU and other places, the question of how will AI change the world? How do we want AI to change the world? What will be the impact on the society that we live in? Those issues came up pretty early on. For example, Hans Moravec was one of the faculty in the Robotics Institute who really pushed the envelope in forcing us all to think about what would happen if we get to a day where there are robots living among us as part of our daily life. Or even if they weren't physical robots, what if they were in our computers and could do things like have real natural language conversations with us, which today we kind of take for granted. But in 1980, many people thought that was a joke, thought it was sci-fi, thought we would never get there. Today, with the rapid deployment of AI in many walks of life, this issue of societal impact is more important than ever.
The first AI system released into the commercial market was in the 1980s. It helped configure and order computer systems based on customers' needs. By the late 90s, Windows had speech recognition software. In the 2000s, Netflix and social media companies started to use AI for advertising and user experience algorithms. Apple released its computer voice assistant Siri in 2011. And a few years later, Amazon launched Alexa. Then came OpenAI, a research organization founded by computer scientists, entrepreneurs, and tech innovators, which launched its generative ChatGPT in 2022. From there, AI catapulted into the mainstream. Think of other generative AI programs like Gemini, Claude, and Microsoft's Copilot. Today, it seems like AI is everywhere. If you had to issue a report card on AI today, how would you grade it?
In technical progress in the last 5 years, I have to give it an A+. We really are in a new era because of systems like ChatGPT and related large-scale AI models that are largely coming out of industry these days. It really is a qualitatively different state of affairs because of the ability to have really conversations with these AI systems.
What about impact on the world? How would you grade AI in that area?
I think we haven't even come close to achieving the impacts that we could already have with the technology we already own and understand. So in terms of taking advantage of this amazing technology, I give maybe the field of AI, but maybe it should be society in our country, a B-. The final area I would score it on is AI risks. And if I had given it a grade 5 years ago, I would have probably given it a C- because there was so little work anticipating what these impacts could be. But today there is much more activity around that. So I guess I give it most improved student in that category.
Thanks, Tom. Fascinating stuff. Okay, let's take a quick break. When we come back, we hear from another trailblazer in the field of AI, who transformed autonomous robotics by holistically integrating perception, cognition, and action. That's coming up on Where What If Becomes What's Next from Carnegie Mellon University.
This podcast is brought to you by Carnegie Mellon University. Located in Pittsburgh, Pennsylvania, CMU is a private, international research university, consistently ranked among the top universities in the world. Its trailblazing research is focused on creating, defining, and accelerating the future of artificial intelligence. For more information, please visit ai.cmu.edu.
Welcome back. You're listening to Where What If Becomes What's Next from Carnegie Mellon University. And today we're talking about the history of artificial intelligence. As we learned earlier in the episode, humans theorizing and imagining artificial intelligence can be traced back thousands of years, with examples showing in Greek mythology. Many in this field cite Alan Turing and his seminal 1936 paper on computable numbers as a key moment in the history of AI. Then, in the 40s, during World War II, computers were built to do nuclear simulation calculations, and the first electronic computer was built toward the end of that decade. But the term itself, and the sort of birth of AI as a scientific discipline, that credit goes to a 1956 convening of researchers at Dartmouth College in Hanover, New Hampshire. Dr. Raj Reddy has been working in AI for decades. He remembers, in the 60s, talking through with his colleagues about a specific aspect of intelligence.
In 1963 was the first time we said there's another component of intelligence, which we all do, where we see and hear and walk with no apparent effort. Even a child can do all these things. What does it take to get a computer to do the same? At that time, we did not know how hard the problem was going to be.
Turns out, it would be a very difficult problem.
And this is called Moravec's paradox. The paradox is, easy things are harder to do, and hard things are easy to do. And for a computer, proving theorems and other things seems to be done even with small computers, but human beings have difficulty. On the other hand, human beings can see and hear and talk and walk, and computers still can't do them.
Reddy joined the CMU faculty in 1969. A few years after his arrival, he and colleagues developed a system to help humans speak to computers. Here's a clip from a 1973 documentary about the system developed at CMU known as Hearsay. Reddy is the one speaking.
To equal human performance, a machine must use all these sources of knowledge effectively. In the Hearsay system, this is achieved by representing knowledge as a set of cooperating parallel processes. Let's now observe the system at work.
Pawn to queen 4. I heard
pawn, 2,
queen, 4.
In the 70s and on, Reddy also did significant work on computer vision and robotics, and was the first director of CMU's Robotics Institute. Reddy went on to win a number of accolades for his research, including an ACM Turing Award. And over the last several decades, as he developed and witnessed the advancement of human-computer interactions, he says his stance on AI has not changed.
AI is just a tool. When we wanted to go faster, we built cars and airplanes. When we want to solve problems and think faster, we use computers. That's as simple as that. It is a tool for enhancing the mental activities of human being. Never have I ever assumed that, even now I don't think, is ever going to replace human intelligence or even come close to the human level.
He gives an example of something human beings do all the time.
Is what we call lifelong learning. There's a memory, there's a continuum. Even after 70, 80 years, I'm still learning some new things, right? And the current systems that learn, deep learning and so on, essentially learn what they're given, and that's it. There's no concept of an incremental continuous learning.
My next guest, Dr. Manuela Veloso, arrived at CMU in 1986 as a visiting student, drawn to the university for its reputation in AI research. She remembers those early years at the university as an exciting period full of possibility, with early AI innovators, including Raj Reddy, who we just heard from, giving demos to packed rooms on things like those early versions of speech recognition systems, or machines that could play chess, even prototypes of self-driving vehicles.
There were no boundaries for what people thought computers could do. It seemed I arrived to a science fiction movie or something in which everybody thought about things that you had never thought before and believed in them. And we all engaged in making these things happen.
Presently, Manuela is the head of J.P. Morgan AI Research and Herbert A. Simon University Professor Emeritus in the School of Computer Science at Carnegie Mellon University. She attributes a lot of her interest in AI and learning about AI at CMU to the late scientist Allen Newell and Herbert Simon. We heard about them and their groundbreaking work earlier in this episode. Manuela, how did those two influence you?
I have never seen anyone so passionate about computers being intelligent like Allen Newell and Herb Simon. Herb Simon in particular, look at this. While the whole world was thinking about optimization, he introduces a concept of bounded rationality, which is this concept that humans don't optimize all the time. Humans are not always rational. If you find a solution which is reasonably good, you don't go and struggle to find the optimal solution for the rest of your life. You are happy with a reasonably good solution. And that changes the way you think about AI, because now you basically have a satisfying way of having algorithms generate solutions. But so I was always fascinated by this concept introduced by Herb Simon and his passion by addressing complex tasks with this way of thinking that solutions did not necessarily have to be optimal, but they need to be solved reasonably well.
And Allen Newell. I heard he had literal boxes at CMU in which he wrote perception, cognition, and action, then agents.
So he was introducing that AI was a discipline of components, natural language, machine vision, all sorts of planning, and then learning. And Allen Newell kind of came up with this concept that unless we integrate all these features, all these components, we wouldn't have the complete AI, the complete agents. So the two of them were really revolutionary and disruptive in the thinking.
Let's talk about your research. Back in the 80s, as a visiting student, you worked with the late CMU professor Jaime Carbonell, who founded the Language Technologies Institute and pioneered the use of computers for translation. The following year, you enrolled as a PhD student in the computer science department, and your PhD thesis was titled One Way or Another by Planning by Analogical Reasoning. What was your thesis on?
So what I did in those days was a very beautiful algorithm in which the way to solve problems, given like some initial state and some goal statement, what we call planning problems, was literally by finding a similar problem that had been solved in the past and then adjusting the solution of the past problem to this new problem. So it was not problem solving from scratch, but it was problem solving by these analogical reasoning, by analogy.
Okay, so this sounds like the basis of machine learning, using past solutions to adapt answers to present problems. Manuela, you finished your thesis in 1992 and then started working with autonomous robots. Not on the mechanical side, but focused on the AI side. Tell me about that.
Yeah, so I grew always up with this understanding that AI was about these reasoning component. Now I usually describe AI as the integration of a component that's like a perception component, and then a cognition component, and an action component. I started doing a lot of robot soccer, in which the robots would need to plan, to coordinate, to achieve a difficult task like scoring a goal. And literally, this world of robot soccer was fully autonomous, meant that no human was involved with it. They really had to actually do all sorts of navigation tasks. It was putting together the sensing processing, the images, the sound, the guidance, all sorts of like input with the reasoning and also with the execution. But what was interesting later is that then I tried doing like these autonomous robots inside of our buildings, performing tasks going from one place to another. And one night, I was like upset that these robots would never be able to do it because the door was closed. They didn't have arms. They only had wheels to move around and cameras, but they didn't have any manipulation. And then suddenly in the middle of the night, I thought, wow, these robots are not up in Mars. They are not down volcanoes. They are not playing a soccer game by themselves. They are surrounded by people. And at that moment, I said, okay, let's do this algorithm in which whatever they can't do, whatever they don't know, they ask these humans, what do you mean? Can you press the elevator button for me? So it was a revolution from my point of view, these kind of what I kept calling this symbiotic autonomy, in which they were autonomous, but in symbiosis with these humans. After all, the humans were around, and ignoring them did not make much sense.
How was it transformative for AI research at that time?
It was not easy to get this across in the AI community because you could be thinking she's cheating. I mean, AI is supposed to do it all. And having these things ask for help did not seem like the real AI kind of like fair way of thinking. But I thought it was the only way to go, because I also got completely convinced that AI, no matter what, to understand your language, to open doors, to pick up objects, would always inevitably have limitations. And so the right solution was to rely on these humans that easily could complement the things that the robots eventually couldn't do. And the goal be how these humans and these machines and this AI can jointly perform better than just the humans or just AI.
That was around the mid-2000s, and you're a professor at CMU. You see these soccer robots on the field as a great scenario to research perception, cognition, and action in a complex environment. But then you take them indoors, and they do learn how to get around the school. So were robots just roaming the halls of CMU?
I literally had more than like 400 visitors being guided by cobots from the elevator to my office. I would also always say, I'm not going to tell you where my office is. Don't worry, there will be a robot waiting for you at the outside of the elevator. So it was true for many years, I mean, at least 4 or 5 years at Carnegie Mellon, that these robots basically guided visitors to my office and then to wherever they needed to go.
And these cobots that help visitors find their way around campus really built upon this concept you introduced, the connection between robot and human, where the robot will seek help from a human. Is that correct?
I introduced is asking for help, and I introduced also this concept of not giving only a demo. These robots were used really every day. So many of the things in robotics were about, like, how do you say, do something that then you demo, or that you actually do some experiments. And we wanted to make them part of the everyday life. That led into a lot of algorithms that require that persistence, that require the ability to really reason about in the long term. So we kept like a lot of data that the robots accumulated. We learned from that data.
And what did you learn?
So there was something very beautiful also that happened with the cobots besides asking for help. So basically, the building has a map, and it has a map of where the walls are, like the architectural floor plans. But the furniture inside of that building, one way or another, changes. Or the people that navigate, they are all dynamically changing. And therefore, we had to introduce a new localization algorithm to take advantage of that dynamic aspect, in addition to the stationary walls. And so those type of algorithms are very novel, and I believe they are part of what is used now to have robots move around in dynamic worlds.
That's it for today's episode. On our season finale, we look to the future and hear from some of these pioneers about where they think and hope what's next for AI.
We're going to see phones that you can set up that will watch you do your morning exercise, or that will watch you cook your dinner. And not only will they give you the next step in the recipe, which they already can do, but they will watch it and they will say, Tom, now it's time to flip the egg, because they'll have vision as well as the recipe.
We'll also explore the risks and ethical considerations as AI becomes more infused into all aspects of daily life.
The end result is not so much replacing humans, but it's changing the way humans work.
There will be some unintended consequences that this technology will create. Then we as a society have to create appropriate regulations or appropriate models so that the damage from such things is as little as we can make it.
That's coming up in part 2 of this episode of Where What If Becomes What's Next. Thanks to all my guests, and thanks to you for listening. Please check the show notes where you'll find links to additional resources for this episode. And to learn more or contact us with a story, idea, or comments, please visit ai.cmu.edu/podcast. And special thanks to Carnegie Mellon for archival audio clips from their 1973 documentary on hearsay with Raj Reddy, Herb Simon at the October 2000 Earthware Symposium, and Allen Newell in the 1991 Desires and Diversions video. If you're enjoying this show, please rate and review us on your favorite podcast site and share with friends. And be sure to subscribe so you'll never miss an episode. You've been listening to Where What If Becomes What's Next from Carnegie Mellon University, where we are exploring what AI means to industries, government, society, and you. Stay tuned and stay curious.